A storage node crashed every 6 hours with an out-of-memory error, but the heap was only 60% used. The culprit? The replication code was buffering entire objects in memory. A single 4 GB object pushed the JVM past its container limit, and the kernel killed it. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover Design Object Storage, Simple Storage Service. Object storage solves the problem of storing massive amounts of unstructured data, backups, media, logs, without worrying about file system limits or RAID arrays. It's the backbone of cloud storage, but building your own means wrestling with consistency, durability, and performance at scale. The key is the only way to locate an object, so key design is critical. Prefix-based partitioning is common, but if your keys are sequential, you'll hotspot one partition. Use hash prefixes or reverse the key to distribute load. Here's how you partition the key space and store metadata atomically in etc. The partition function uses the first byte of the SHA-256 hash to assign a bucket. The metadata put uses an etc. transaction to ensure atomicity. Once you have the key, you need to decide which storage nodes hold the object. Instead of a central location service, use consistent hashing with virtual nodes. Each node gets multiple points on the hash ring. When you write an object, you hash the key and find the next n nodes on the ring. This code implements a consistent hash ring with virtual nodes. The addNode method creates virtual nodes by hashing the node ID with an index. getNodes finds the next n unique nodes on the ring for a given key. The metadata store maps keys to object locations, sizes, checksums, and version info. It must be strongly consistent. If you put an object and immediately get it, you should get the new version. Production choices: etc. for small clusters, CockroachDB for geo-distributed. Here's a metadata schema for CockroachDB. The objects table stores key, size, checksum, locations, and version. The atomic compare and swap update ensures conditional puts work correctly. Object storage often promises read-after-write consistency for new objects, but eventual consistency for overwrites. In practice, use a last-writer-wins strategy with wall clocks. Each replica stores a version timestamp. When reading, the client fetches from all replicas and picks the latest version. This code shows last-writer-wins reconciliation. It fetches from all replicas and picks the one with the latest timestamp. Simple, but relies on clock synchronization. Mitigation: use logical clocks. Nodes fail: use a gossip protocol for failure detection. Each node periodically pings a random subset of others. If a node is unreachable for 30 seconds, mark it as suspected. After another 30 seconds, mark it as dead and trigger repair. This simplified gossip-based failure detector checks heartbeats. If a peer's heartbeat is older than 30 seconds, it's suspected. If older than 60 seconds, it's declared dead and repair is triggered. Object storage performance is dominated by network and disk I/O use SSDs for metadata nodes, HDDs for data nodes. Cache popular objects at the edge with a content delivery network. Split partitions when they exceed a threshold like 10K objects. Use a Bloom filter to decide what to cache. If the key tests positive, serve from cache. Otherwise, serve from storage and add to cache if it becomes popular. Object storage is often exposed via HTTP APIs. Authenticate requests using HMAC signatures like Amazon Web Services Signature v4. Authorize via bucket policies. Encrypt data at rest with AES-256 and manage keys with a key management service. This simplified function verifies an Amazon Web Services signature v4. It rebuilds the canonical request and compares the computed signature with the one in the header. This is the same issue we highlighted at the start. Here's exactly why that happened. The replication code was loading entire objects into memory before sending them to peers. A 4 GB object caused the JVM to exceed its container memory limit and get OOM-killed by the kernel. The node crashed every 6 hours. The fix was to stream objects in 1 MB chunks instead of loading them entirely. We also added a per-node memory limit of 512 MB for replication buffers. This prevented any single replication from consuming all memory. This is the exact mistake from the incident. Using IOTIL, read all on a 4 GB object causes the entire object to be loaded into memory, leading to OOM-kills. Always stream in chunks. Using timestamps as keys like 2024-0101 object will hammer a single partition. I've seen a cluster melt because all writes went to one node. Always hash or reverse the key. Always make replication factor configurable per bucket. Some data needs n equals 5 financial logs, some can tolerate n, cached thumbnails. Don't hardcode n equals 3. Never store object data in the metadata store. That's how you run out of space and crash the cluster. I've seen a team store 100 MB objects as etcetera values. Etcetera has a 1.5 MB limit per key. They learned the hard way. When a node fails, all its replicas need repair simultaneously. This can saturate network and disk I/O, causing cascading failures. Throttle repair to 10% of bandwidth. I've seen production code with Amazon Web Services keys hard-coded in a config file committed to Git. Use a secrets manager like Vault or Amazon Web Services Secrets Manager. The article uses etcetera for metadata, but etcetera has a 1.5 MB key value size limit. For object metadata, e.g., locations array, ensure each entry stays well under this limit, or switch to a distributed SQL database like CockroachDB for larger metadata. The article mentions streaming in chunks, but doesn't show code. Here's a Go snippet that streams an object in 1 MB chunks during replication, preventing memory exhaustion for large objects. When a node fails, repair can saturate network bandwidth. Always throttle repair traffic, e.g., limit to 100 Mbps per node, and prioritize repairing smaller objects first to minimize impact on live traffic. Here are some debug commands. Use iostat to check disk I/O, use ping to check network latency. Use curl to check replication queue metrics. Let's run through some common interview questions. How does consistent hashing handle node additions? Only when n keys move due to virtual nodes. When choose eventual consistency. When write throughput is paramount and stale reads acceptable. What happens on node failure during write? Synchronous writes succeed on remaining replicas. Async may lose data. And a few frequently asked questions. How to design object storage? Flat namespace, consistent hashing, replication, strong metadata store. Difference from block storage? Object, HTTP, flat, cheap, high latency. Block, mounted, low latency. How to handle concurrent writes? Last writer wins with timestamps or conditional writes. To recap, object storage is a flat namespace of keys and objects. Separate metadata from data to scale independently. Use consistent hashing with virtual nodes for even load distribution. And always stream in chunks to avoid OOM-kills on large objects. Ready to go deeper? Up next, design a proximity service, then design Ticketmaster, then design a distributed job scheduler. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.